looking at code follow along.
Right, so as Tanner mentioned, I'm going to talk a little bit about analysis in Python with these n-tuple files, and very specifically, I'm going to talk about using a tool called uproot, which is a very, very light version of basically it allows you to interface with these root files without having to go through the process of installing the entirety of root, which has its own benefits and advantages depending on what type of tasks you're trying to do. You can save yourself a lot of time having to deal with environments and all this stuff by just installing uproot. So the tools that we're going to be using, as I mentioned, uproot is sort of the most crucial thing for what I'm going to be talking about in these slides and this bit of example code. And there are a couple of things that aren't strictly required, but are extremely useful, and I highly recommend installing them. The first of which is awkward array, which allows you to basically handle some of these, as it's implied in the title, awkward data structures. Oftentimes, when you load lots of data into Python, you do so using NumPy, which is very useful, and I love it very much. But it doesn't really handle data with ragged shapes. It likes things that look like boxes and squares, not things that have a varying number of samples per event, for example, number of photoelectrons collected per event. And then just a tiny bit of matplotlib. And the idea here is to stick to as close to pure Python as we possibly can. So I'm going to very, very briefly go over opening these files, inspecting them, and plotting some data, just as a zeroth order thing to get you started and sort of act as a launching point to the interactive session later, where we sit down and sort of go through this all together, or individually, depending on how we want to structure it. So the materials, as Tanner mentioned, on the Slack channel, I've uploaded an example n-tuple.root file. You can very much generate your own, and I encourage you to do so, but there's an example file there already made. I have a Jupyter notebook, which if you're familiar with Jupyter, great. You can just load that in and open it up after installing the dependencies. If not, there's an HTML file that you should be able to just open in your browser and see the individual Python code and be able to copy paste that wherever you like. And that's sort of like the helper module. So if you don't have things installed, I would recommend making sure that you have Python at least version 3.9, something reasonably modern, and adding these dependencies by running this command, pip install, and then you have to basically tell Python to go out and grab uproot, awkward, matplotlib, and numpy. And once you do that, you can relatively easily check that things are installed on your Python environment by running this one-liner in the command line itself. You can use Python C, import all of these, and then just, for example, print. Right now, I just have the awkward version and uproot version, which are the most important. But you can go through and check each of the versions of these just to make sure we're all kind of on the same page. But really, as long as you have uproot 5 and awkward greater than 2, you should be fine. So I'm going to give a very, very quick recap onto the highest level structure of these files. As Tony mentioned, there are these different trees. They are the meta, the output, and the waveform trees. And then I'm going to talk a little bit, before diving into the code, a little bit of my own personal Python philosophy on how you should actually be storing these structures in Python. It's sort of a thing that people say, Python's slow. And in certain cases, it can be. But if you're careful about how you choose your data structures, you can get C-level performance out of Python code. And the choice between how you store your data sort of dictates that. And then finally, I'll go over some very basic operations in this example file itself. Just navigating the files, how do you open them? And producing a very simple histogram as a sanity check. This is sort of like the very first line of debugging debugging your outputs beyond using the visualizer. And then we can open and manipulate the contents of these events, in the session later. There's a recap of the n-tuple trees. The first of which is the meta tree. This is all information that's generated once per run, and it includes things like the macro file itself, so you know what was actually used to generate this file, and other things that you sort of set once for a run and you're done with. So for example, you can look at the list of PMT IDs, and I have it written here twice, which doesn't necessarily need to be written there twice, but it is. It's important. The PMT ID to position map. What it should also say is the PMT ID to direction map. Because once you have your geometry set in rat, it's kind of there for the remainder of the runs. You store this geometry, this high-level geometry information in the meta tree once, and this is where you access these things. You don't need to go each event and check to see if the geometry has changed based off of how the way ratpac operates. The next tree is the output tree, and this is where all of your per event data lives. So things like PMT hit times and charges, event truth information, what was the particle gun used to produce this event. And you can add lots of optional flags. This is one of the places where a lot of data can live, and you look through the various options depending on what you want to do with your analysis. You can sort of like make this middle column bigger, smaller, depending on what you're actually interested in saving from ratpac. And then finally, something I sort of very briefly gloss over because it's a higher this topic is a sort of more advanced, but it's definitely worth noting, is the waveforms tree. So these are generated once per event, and they are typically very expensive to save because if you have a waveform for a number of PMTs per event, you have this giant block of data with tons and tons and tons of values. But this tree stores things like the digitized waveforms and where pulse times align in these waveforms, and is useful for sort of more complex analysis on detector data. And you can expose that once again by accessing these flags in your macro when you generate these n-tuple files. So actually handling this data, there are many, many, many options in Python for manipulating the data once you sort of have it open. And there is no one truly correct way to do so. But in my mind, sort of the things to think about when you're performing some analysis in Python are looking at, first and foremost, what is the shape of your data? And then basically, how important is the speed of processing? You can very easily in Python trade readability for speed. And depending on how much data you're actually looking at, who cares if you have a slow loop if you're only looking at 10 pieces of data. And then finally, readability and flexibility. So as I mentioned, this really comes down to the shape of the data and what's inside of your data. So going from left to right, you have things that are less flexible, but more fast, typically, to things on the right, which are very arbitrary. You can sort of put anything in these structures, but typically they're a bit slower and you have to use them a bit more sparingly, especially if you're looking at a lot of data. So NumPy is suited for data with rectangular shape and everything that has the same type, which is kind of represented by this, green square grid, and everything's nice and orderly. You could imagine things like, especially in the meta tree where you have the geometry, that's sort of static, fixed, that can very easily live in a NumPy file, or a NumPy object, and you can do manipulations on that. It's fine. Moving on, sort of an intermediate balance, and actually the default for uproot is this awkward platform, which can handle structures that have a little more complex shape, but really it's most interesting for things where you have like a list of vectors that change length from event to event. So as I mentioned, the number of electrons, photoelectrons you see in a PMT very frequently changes, and awkward allows you to handle these sorts of things, whereas NumPy would require things like zero padding, which is annoying. You can do it, but I recommend against it. And it has some of these vectorized calculations to speed things up still. And then finally, at the highest level, you have sort of Python native structures like dictionaries, lists. And these can actually contain the previous two objects. You can take a Python list and put NumPy arrays, you can put awkward arrays, you can put whatever you want in them. You can have a list of lists. These are very, very arbitrary. You can put whatever you want in them. But usually this is sort of like the highest level of management in your code. This is what things would live here, or things like macro files that are just strings. So diving into what NumPy is very briefly, if you don't know, once again, we're looking at things that are regular and homogeneous. Uh, think rectangular shape. The technical terms are, like fixed rank, contiguous. But the main advantage of using these sort of objects is that they really are kind of like C++ vectors under the hood, if you're familiar with that. So they enable basically you to use very, very fast calculations and perform things like dot products over millions and millions and millions of uh, uh, pieces of data in your structure very, very quickly. And these are great things for scalars, fixed length vectors, and they have the lowest memory overhead. So if you're doing something with a large amount of data, try to use these first. And this is sort of like this philosophy of using vectorized structures is essentially why things like machine learning techniques are generally implemented in Python, where you have some nice fixed shape data and you can pass it to some function where someone has gone through the excruciating detail of writing a very fast function that can perform these operations like dot products, sums, averages, and it'll do all of these things for you. Moving on to awkward, it extends a lot of NumPy commands, if you're familiar with it, to these jagged structures. And this is how you typically read things in if you're not really sure what you're actually looking at in these n-tuple files. There is a bit more overhead compared to NumPy itself, but this is also a great option for the majority of the data you'd find in these n-tuple files. But you still really want to make sure the hardest constraint here is making sure that all of the data inside of this is the same. You don't want to have things like integers mixed with floating point data types in these shapes, as that makes things complicated, slows them down. You lose a lot of the benefits if they're not of uniform type. And then finally, the lists, dictionaries, stuff like that, they can hold arbitrary objects. And in some cases, they actually are faster than the previous two structures. As a matter of fact, things like lists are excellent for resizing. If you have no idea how much data you have, you can very easily change the shape of lists. Whereas if you take a NumPy array and you use a for loop to basically add vectors along the way, it is really, really slow because it ends up sort of like taking that entire bit of data, wiping it, creating a new space, and filling that list in. Whereas Python does some intelligent coding under the hood to allow you to resize these things. So, these rules aren't strict, and it requires a bit of practice to understand, what data fits in the best container. But, the rule of thumb here is to keep small, irregular data in lists and dictionaries. And, if you are loading data and you don't know the shape, you can put it in a list at first. But once you start performing actual calculations and you know what the shape is, sort of freeze it in place and then pass it to one of these other structures so that it runs in something that's closer to like compiled C rather than arbitrary Python. There's lots and lots and lots you can do with these files. You can extend it. We just had a talk on some of that, and there is documentation that Tanner wrote on these files to give you a better sense of what all is inside of them. I highly recommend giving it a look. The link is there. And here, before diving into an actual interactive coding session, I'm just going to open up what I had posted here on Slack. So the n-tuple file that I had provided, I basically just took all of the optional flags, up here, visible to you, but this block of ratpac set things at the top, I basically just enabled all the flags, which is not a bad thing to do for these initial runs. Just put everything in the files, see what's inside, play around with it a bit. Make sure that you have an environment prepared. I just listed here the very basic install instructions that I had listed on the slide. If you don't already have Python set up, make sure you do that. And then you can do things like create a clean virtual environment. You don't have to do it. I recommend it, but details. And then basically you just have to go through and import all of these things that I had just mentioned on the slide: uproot, awkward, numpy, plotlib. You go through, print the versions, verify that things look all right. And really, what I'm going to take a look at here is how you can navigate what's actually inside these ntuple files. It's very easy in Uproot. I'll show you an example of that, and just sort of walk around, read some of these branches, read things like scalars, vectors, make a quick sanity plot, just as some example code showing how you can open them, extract some of this data, perform some vectorized operations, and plot a histogram. And then save the data in a different format. So for example, if you need to give data to someone else who's unfamiliar with ratpac and ntuple files, you can pretty quickly take sections of data and save them in CSV files, which is not the most recommended way to save data, but in a pinch, it can be useful. So once you have everything imported, zoom in a little bit here. The most important thing to specify, obviously, is a file path. And actually, opening the file is as simple as just saying uproot.open, and you give it the file path. And that gives you the file object. Now, when you do this, it doesn't actually open all the contents and load it into your computer. So if you have a giant ntuple file, you don't have to worry about this sort of crashing your computer with tons and tons of data. And this is one of the advantages of using Uproot, is that this is just telling Uproot where to look for this file. And then the highest level inspection you can do is take this file object and print its keys. And you can see if you do this, for this particular example, I enabled all of the branches of the ntuple file and all the trees. You can see there's a meta tree, an output tree, and a waveform tree. So that's good. So to access each of these, you take this file and pass it the key name. So we have our ntuple file, and we want to access the meta branch. You basically close it in brackets with the string calling the particular branch itself, for example, meta output, and you can call these by their own object name for convenience, and then sort of browse from there. So instead of going into the T browser and clicking on the file and looking at all of the contents, this is sort of the equivalent of that, is adding this key, saving it as a variable. And then you can sort of step down once again. So you can then print everything that's in the meta branch. So here's just a simple for loop where I say generate a list of all the keys in the meta branch and then print all of these. So if you look at the documentation, this should match what is online. And you can see, you can really just pull up everything from the run IDs, PMT types, the PMT orientation and position, so on and so forth. And you can do the same thing for the output branch. And this code also works for the waveform branch, which I highly recommend if you're opening this file and playing around with it. Looking at this cell, and the comment isn't super useful. I should say, try it yourself and add a bit of code that prints out the waveforms branch. So you don't have to open, you don't have to use root to sort of open these things up. You can just use Python to navigate these files. So now that we have a sense of how we can sort of inspect the high-level contents, let's actually read some data in. So once you actually have these different branches or trees loaded in, like for example, this meta here, you can actually access the data inside by calling the file and the tree itself, putting a dot here and then saying arrays. And that's telling Uproot to go into the file and actually grab the data from inside the file. So here is where you start actually loading things on your computer, where you'll start putting data on the RAM. So here, if you just, you can pass it different arguments. Here, I just by default said pass it as a NumPy array. You can change that by changing the string keyword here from NP to AK. This is all sort of in the docs, but just to get started, this is good enough for now. And we can print things like the run ID. So just have some print statements here where say, this run info that has these NumPy arrays, grab the key run ID and produce the first value. And you can see you have a giant list of these things. Some of these vectors are wrapped, so you have to be careful with the dimensions sometimes. So you can see in the output here, the PMT ID array is actually a list with values inside of it. So if you just want to access the data itself, you want the 0th entry. So I've then printed it again with the contents of the array. And here you can see that there's an event sequence counting up from 0, which you should reasonably expect. And then we can do something that's probably a little more useful for analysis. We can extract from these PMT IDs the PMT positions. So, we can go into this run info, which is the meta branch, and then say grab the PMTX, PMTY, PMTZ. And this is sort of the neat thing about NumPy if you haven't used it. You can take these PMT IDs that we've extracted from this file and basically put them in these arrays for PMTX, PMTY, PMTZ, and then print all of these out to get a table of the PMT IDs and where they're positioned. So, this is sort of how you access the geometry of the detector in these n-tuple files. And here I just limit it to the first 20, but you can change this and have it print out everything. And this is how you access this data. Another point for people to write their own examples, maybe learn a little bit more. You can modify this code instead of printing out the positions for each PMT. If I scroll back up here, you can see that there's this PMT XYZ, and there's also this PMT UVW. And PMT UVW corresponds to the orientation of the PMT in space. So, scrolling back down here, using this information, you should be able to extend this print statement to not just have the position of the PMTs, but its orientation. Okay, so now that we've taken a very, very brief look at measuring this or reading in this static data, we can look at things that are a little more complicated with awkward. So the process is kind of the same, but instead of looking at the meta tree, we're saying we want the output tree, which contains our event data, and we want to get the arrays from that. And here, because this output data can become very, very large, I specify that I only want certain keys to be loaded in. And in particular, the keys that I chose were the MCID, which is the Monte Carlo event IDs, the N hits for each event, MCPE front-end time, which is essentially the time that a photon is registered in a PMT after applying some transit time spread, and the IDs associated with it. So you can sort of map all of this event information back into a real event structure that's useful for analysis. So once you do that, you basically change the library from NumPy to awkward, so you can handle these variable length hit arrays. And here's just a very small snippet of code that accesses an event and then prints some of this information out. So here I just have this variable event. I just chose event 6. And I printed out the MCID. This is just sort of a sanity check. Event 6 will return event 6. That's good. And then we can look at the number of PMTs that were hit in that event, which is that this event N hits, and then we reference the event number there. And for this particular event, we had 12 PMTs with some sort of measurement inside of them. And then if you want more information about it, rather than just this high level, here's how many PMTs were hit, we can look at this MCPE front-end time to see when all of these photons arrived, which is this third vector here. And you can see that there are a number of photons at around 17 nanoseconds from the event start time, with what I believe is a dark noise hit at the end, because that's quite a large number. And then below it, to make some sense of these PMT times, to give it that spatial information, we can extract the MCPMT IDs. And these MCPMT IDs actually correlate to the thing I talked about earlier up here. This table that you generate can be used to say, okay, PMT 78 was hit. What does that mean? You can go back up to the table that you generated from this meta tree, look for PMT 78 and say, the PMT in this location of the detector was hit at this time. And you can use this information to slowly build back up your event structure, depending on what information you actually need. So once you have this data, you can use for loops to access these things event by event. But here's a super basic example of vectorization. So we have this N hits. Let's say we have our series of events. We want to know how many PMTs we had hit summed across all events. you can use awkward and its vectorization functions to quickly perform these things without having to use slow for loops. So here you use AK, you call awkward, and you say, I want to sum everything in the n hits vector. Happens very quickly. I mean, this is kind of overkill. It's not a huge file. You could use a for loop, but it gives you the total number of n hits over the file, which, great. But n hits isn't really the same thing as the total number of photons collected. N hit just says, did a photon hit a PMT or not? It doesn't count how many were in a single PMT. And we can check this by taking the sum over all of these front end times. We can basically, oh, actually, I shouldn't have summed the times themselves. I should have summed the lengths. But you can sum other vectors here and sort of, this is the sum of the time, which isn't very useful. I guess you could divide by the number of events and get an average of n time. But you can use these vectorized operations to act on these vector-like objects. And here's like an example of a quick histogram. So we can look at the number of PMTs hit per event over the events in the file. So once again, you can access this event n hits, create your histogram in matplotlib, specify the number of bins, the type, and you can very quickly see, okay, how many PMTs were hit on average and the distribution of such in this event. So you can see a lot of events have nothing in them. That's fine. But, of the events that did have something going on inside of them, you can see that the average looks to be about, 11 PMTs hit per event with a tail out to about 20. And these are very useful for very quick inspections of what's going on inside your files. You can use event loops when you need to iterate. Usually you can find some vectorized instruction to do this. But if you're doing something very simple, let's say we have this histogram and we want to look for sort of events that had a large number of hits, we can create a for loop across these events and say for if we have events above 20, we want to print which event it was, how many hits it had. So here is an example of me just saying if the number of n hits is greater than 20, print out that event ID and print out how many hits it had to just sort of give you a sense of, where was this event on the right-hand tail of this distribution. I'll get back to you about task 6. I messed with the code, I broke it, but you should be able to get the macro file back out in Python. It's a little clunky. It is there. I'll get to work on that. And then finally, if you want to, as I said, send this data to someone else who has no idea what an n-tuple file is, here's a very simple example using pandas, where I take the event n hits and the amount of energy deposited in the scintillator, which I believe is nothing in this particular file because it had water. But create a CSV with these quantities. You can define how many rows you want. You can slice the data and go on from there. At the bottom, I have a couple of suggested exercises, but I think really, after this talk, if people are interested, you can join this session, I believe, in the other room. Is that
or yeah, maybe we'll use the projector here or something. Yeah.
Okay. Yeah. These are just some suggestions, but really, I think if you're sort of interested in a more hands-on approach to everything I just talked about, open up Python, start playing around with it. Try to read the files, get different data, plot it, print it, just play around with the data, see what you can do, and we'll be happy to sit down and answer any questions you have. And if there's something particular that you're interested in extracting from the files, don't hesitate to call me over and say, hey, I want to do this specifically, and I'm happy to sort of walk through an explicit example doing that task. With that, I think I've rambled enough. And we can stop this presentation unless anyone has any questions before. Yeah.
A quick one. So you loop through to get the keys and then pull the arrays that way. I was curious how that compares to loading in the file as an R data frame and then pulling columns. If you know.
Is that R data frames? What is an R data frame?
It's a table-like structure that Root has implemented. and you can load root files directly into that, and it basically makes it allows for columnar analysis.
Oh, yeah, so I try to avoid root as much as possible, so I am not the best suited person to answer that question. I'm assuming if it's something that is written in Python, is it something that you like import root and then you can just like call that function?
Yeah.
I'm assuming it's a similar, yeah, it's gonna have a similar speed to that sort of structure.
Our
It's
data
just-
frame is heavily inspired by upload and index. So it's just root's response to the fact that everybody's starting to upload.
Okay, yeah, so I think that, what James just said, as long as you're using these functions to actually handle this sort of misshapen data, it's hard to go wrong. It's just a matter of, do you need and want the full install of root and all the tools it provides? Or do you want just like a 2-second, pip install? I just want to open the files and then, export it to something else. It's just a matter of philosophy. And I think Tanner has some examples that he posted on the channel that use the full PyRoot if you want to go about it that way. Yeah.
Follow up on your comments that you try to avoid using root as much as possible. I think we're in the same camp. And so the question to developers is, can we avoid saving into root entirely and just use comma separate value format?
Yeah, that's 100% feasible. Really, what we've been talking about are two default data structures. So the outroot files and the out ntuple files are just two examples of processors that let you export data from ratds itself. You could very easily, it's straightforward to basically look through the way those files look at the rat data structure and then read it and then export it to a file. And say, for example, you want to make like a SQL database and just have that be what you export. You could just write a processor called like out SQL, and then you would call that in ratpac, and it would export the data in whatever format you want. It's just a matter of knowing the C code to access the ratds, grabbing that data in the C code in the processor, and then having that processor dump it out to whatever format you want.
Right, but as you say, it's straightforward, but maybe it's something the developers can implement in the future version of ratpac.
So, comment as a developer is that as annoying as root itself is, the root data format, the file format itself is highly optimized and there's nothing better than it. And uproot is a piece of Python code that allows you to very easily convert it to something else. Root has done very thorough benchmarking on their data format and has shown that whether you're talking about HDF5, Parquet, SQL database, nothing performs better than root in terms of file output, especially for heavy spending developers. So I think the plan for development, I don't want to speak for the whole coordination group, but I think personally, I would think that coupling ourselves to the root data format, the ntuple format, I think it's a continued plan of development just because it's so highly optimized for exactly what kind of data we want to store.
I agree with what James is saying, but what we need to do is provide more examples for how to open that data format easily in Python and in C++. And those examples don't exist yet, but we're starting to write it.
If I can add, as a new user of ratpac, it really is quite easy to define a processor that writes out to CSV. I usually do that because I usually need like 1 or 2 variables, not all the things that root gives me. And so I have written things that just write into a CSV, and it really is pretty straightforward.
But my point is you need uproot or pyroot.
No. In ratpac itself, you can write a processor that just takes the values from ratds, as Brett Garrett said, and just dumps in the CSV.
And also uproot is just a dependency. There's no dependency on root itself. It's completely a separate piece of code that just talks to the data format.
It's kind of like, I guess we could probably discuss how it would be best to include an example of how to do this. But in my mind, if you have a sense of how to open the outroot files, that structure is basically the same thing. If you can open that outroot file, that is how you would basically write some C code as a processor, and then you would take that data and then just import whatever data format you like, and then export that. So I guess it's just a matter of when we document it. Do we have any documentation for Outroot yet?
A good one. But if someone wanted to write out CSV, a processor that did out CSV, something simple like that, that would be welcome. I mean, it's just a feature that would be happy to add. I don't think any of the people in this room are planning on writing that processor right now, but if someone wanted to do it, sounds like there would be interest.
Yeah, the only time you run into trouble is if you have a variable that doesn't already exist in ratds that you want to export. That's when things become difficult. But that's sort of that's more of an edge case. But if you're that far into it, you probably have a sense of what it would take to extract that data, and that becomes more of a project.
Gabriel, do you know lunch is arriving soon, or?
It should be here by past.
Okay.
On that note, the veggie pasta is for the vegetarians and vegans. So if you're not vegetarian or vegan, please leave it until everyone has had a chance to have fun. There should be plenty for the meat eaters.
Okay, and then just, we can hang out and start the workshop while we wait for lunch. The session I'll be sort of running after lunch is really, if you just had no idea what Garrett was talking about, you're like, I want to get more of a basic understanding of what's going on. I'll be helping people, anyone who wants to just come sit with me, helping people get past the basics rather than getting to where Garrett's talking about, which is, I think, a couple steps past the basics.
And again, I might propose you guys check out the,
Oh, yeah, we could
over there.
We could maybe go sit in that other room, yeah.
Just check it out if it works.
Okay.
If that works.
Sounds good.
Do a lot of people not want to develop with package?
Files.
Yeah, because that's what I've used for the last 3 years. I was just curious why it seems like a lot of people are very apprehensive to use it.
So
Yeah, it seems very efficient.
the file format itself, it is wonderful. For everything else, like, not so much. Like there's a lot of overhead or cement and one. Like we've had issues with it through the years. Probably it's resolved mostly now, but like so the root format is interesting. It just adds over
different scaffolding. Obviously, it's very helpful that you fit it from the macro.
absolutely.
Yeah,
So,
it's like
I personally, I call it fun. I'm all about the. It is.
What is the complexity?
There's no real. A lot of people want to say files in HTML.
Oh, right.
Which there's probably reason 15 different methods of decision. Like I was looking for a song.
Yeah.
And the actual encryption, not encryption, but the way that everything is encoded. It's a very session. Okay. So that's why we're kind of tight to it. But then like, yeah. So it's not a very good explanation, but it's, yeah.
You're not saying.
So when you say overhead, is that as in just like time to learn and use it, or like overhead in what sense?
In the sense that, I mean, there's functions to do meaning optimization, there's a lot more functions outside of just saying you're done.
So there's like, this submits 32 jobs at a time. It's 5-minute delay, submits 32.
But then, yeah, I mean, it's like you could do that in Python now as well. So like, which one do you want to do?
Because that's what I'm used to doing. I'm used to analyzing data in C++ or Python.
Oh, actually, let me.
I was curious if there was like a computation